And welcome to this lecture presented by Onyx on eigenvalues and eigenvectors. Today we're going to move on from some of the other linear algebra topics that we have discussed and dive into eigendecomposition. Eigendecomposition is going to be much more complex than some of the other topics we have covered up to this point, but that's okay. We're going to let Python do some of the heavy lifting for us when we actually do a project on eigendecomposition. And instead, in this lecture, we're going to focus more on the theory. What is an eigenvector? What is an eigenvalue? And what are they used for? That way, we can have a good combination of knowledge of the theory and motivation behind eigenvectors and eigenvalues, as well as the functional capability of calculating them using Python. In this lecture, we're going to talk about eigendecomposition. We'll explain eigenvectors and eigenvalues, what they are. We'll talk a little bit about some of the necessary matrices that go into finding eigenvalues and eigenvectors, such as the identity matrix and the inverse matrix. And then we're going to move on to some of the properties of eigendecomposition and conclude with the motivation for eigendecomposition, which, spoiler alert, is going to be principal component analysis. All right, so let's go ahead and dive right in. Sorry about that. All right, here we go. So eigendecomposition is simply breaking mathematical objects into their constituent parts. So many mathematical objects can be understood better when they are broken down into their constituent parts like this, or by finding some of the properties of them that are universal or not caused by the way we choose to represent them. For example, integers could be decomposed into prime factors, such as the number 10 could be represented or written as 2 times 5. From this representation, we could conclude useful properties. For example, that 10 is not divisible by 3, and that any integer multiple of 10 will also be divisible by 5. So integers broken down into their prime numbers. Similarly, we can decompose matrices in ways that show us information about their functional properties that is not obvious from the representation of the matrix as an array of elements. And that is essentially why we do eigendecomposition. So in this process, we're going to take a matrix and we're simply changing the representation of that matrix. We're going to break it down into eigenvectors and eigenvalues. These eigenvectors and eigenvalues are going to describe the matrix just as 2 times 5 could be a representation of the number 10. We can have eigenvectors and eigenvalues as a representation for our matrix. But what are exactly the eigenvectors and eigenvalues? Great question. Let's talk about that next. So the eigenvectors are the vectors that the linear transformation A here, A is a square matrix, merely elongates or shrinks, and the amount that they elongate or shrink is by the eigenvalue. So this equation here is called the eigenvalue equation or the eigenvalue problem. So we have a matrix A, and the eigenvectors of that are going to be the V here. That's the bolded V to denote the vector. And the eigenvalue is going to be lambda. It's a scalar. And actually, this is going to be a vector of scalars. Here we are going to have an eigenvalue for each individual eigenvector. So each eigenvector has an eigenvalue. The eigenvector, just to say it once more, is a vector that can be multiplied by the matrix A, and it doesn't change its orientation or anything like that. It only changes the scale. So it's going to shrink or expand the vector, and then the amount that it shrinks or expands or scales is going to be by the eigenvalue, lambda here. Okay. So here's just a visual representation of that same process. Here we have 2 orthonormal eigenvectors, V1 and V2, and these are going to be eigenvectors for the matrix A. When we multiply these vectors and this complete unit circle here, we have this circle normalized to a magnitude 1. It's called a unit circle. If we multiply it by the matrix A, we are going to expand one of the eigenvectors. So you see V1 grows, and V2 actually is going to shrink. And they're going to expand or shrink by lambda 1 and lambda 2 respectively, which is the values that correspond to those particular eigenvectors. So I think this is a great way to intuitively understand these. It's nice to see a visual representation of what's actually happening mathematically. All right, so that brings us to eigendecomposition. If a matrix A has n linearly independent eigenvectors, we can form a matrix V with one eigenvector per column and a vector lambda for all the eigenvalues. So this is similar to what we saw. However, we can now find the eigendecomposition of A then using the following equation. So here we have the matrix A is going to be equal to V. Remember, V here is a matrix with one eigenvector per column. And then we construct a diagonal matrix out of all of the eigenvalues and multiply that by the inverse of all of the eigenvectors. So we have a diagonal matrix. We've talked about the diagonal matrix in our lecture on special matrices and vectors. However, we didn't really mention the inverse matrix, so we can dive into that a little bit right here. But in general, this equation is how you would find the eigenvectors or eigenvalues. And this is a great way to break apart a matrix into these constituent parts. All right, so the inverse matrix, here is the equation that actually satisfies the inverse matrix. So the inverse matrix is going to be any matrix that we can multiply the original by and get back the identity matrix. So I here is the identity matrix, and an identity matrix is simply a square matrix, 2 by 2, 3 by 3, 4 by 4, etc., where it has ones on the diagonal, 0 elsewhere. So it is a diagonal matrix, but more specifically, it is called the identity matrix. And this is very similar to a reciprocal for integers. For example, if you had the integer 8, the reciprocal of 8 would be 1/8. Multiplying by that would get back 1. You could think of 1 as, a 1 by 1 identity matrix for an integer. So when we have a matrix here, we're going to get back ones on the diagonal, get back the identity matrix corresponding to the appropriate size matrix. We're not going to go into how you find the identity matrix mathematically. It really isn't that difficult. It involves dividing by the determinant and switching a few values. Really easy to do in Python, though, so we'll take a look at that as we explore eigendecomposition in Python in a project. I just wanted to give you this information about the identity matrix because it is important to understand the inverse matrix when we're talking about eigendecomposition. All right, so here are some properties on eigendecomposition, and there's a lot on this slide, but really the most important one to pay attention to is the first one, that not every matrix can be decomposed into eigenvalues and eigenvectors. More specifically, you really need the inverse to exist. And if the inverse does not exist, then you're not going to be able to calculate some of these eigenvectors and eigenvalues. And so there's some conditions that go into the inverse not existing or existing for particular matrices. We're not going to go into those details too much because it isn't necessarily fundamental knowledge for machine learning. We can do a lot of this in different programming languages, and they're going to tell us just fine whether or not we are capable of finding the inverse or doing eigendecomposition. Some more properties about these is that they sometimes are referred to by their names. So if you have a matrix whose eigenvalues are all positive, you would get a positive definite. A matrix whose eigenvalues are all positive or 0, positive semi-definite, and so on and so forth. We have negative definite and negative semi-definite as well. You might hear them referred to in those names. However, it isn't quite as common as just actually writing out the entire eigenvectors and eigenvalues. So you may see both in the literature as you're going through different machine learning papers. All right, and one last thing, why? Why do we need eigendecomposition? Well, the main motivation for eigendecomposition in the context of machine learning is going to be principal components analysis, PCA. And PCA comes up quite frequently. It's simply a statistical procedure that is used to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. So this is a great way to condense or compress a data set. You can take high dimensional inputs and convert them into a lower dimensional representation using principal components analysis. There's some cool work that's been done with PCA to do visualizations of high dimensional clusters using a principal component analysis such as this. But it, in general, is a method of summarizing the data or compressing the data. And it can be found using eigendecomposition. Eigendecomposition is actually one of the fundamental steps in principal component analysis. There isn't actually much learning in terms of machine learning that's going on in principal component analysis, in that we don't really have to update parameters iteratively to improve performance. However, it is used as a machine learning technique, and that is why eigendecomposition is important to understand fundamentally, because you will see this if you are studying machine learning, whether it's at the start or later on. Principal component analysis will come up, as well as data compression in general. All right, so that brings us to the conclusion of this lecture, and actually the conclusion of the lectures for Unit 1 as well. So I hope you have a decent understanding of some of the linear algebra behind machine learning techniques up to this point. And again, we're going to practice these in a project in Python using NumPy, so that can help reinforce some of the data that we've talked about in these lectures. Thank you very much for listening.